Okay, here we go with Chapter 1, Section 3. And we are looking at physical and chemical properties, Chapter 1, Section 3. In this section, we are going to identify properties of and changes in matter as physical or chemical. And we're going to identify properties of matter as extensive or intensive. Oop, one too many slides. Okay, in this section we're going to take a look at physical properties and physical change. Now first, what does the term property mean? Well, a property is a characteristic that enables us to distinguish one thing from another. Okay, that's simply what a property is. Now when we talk about physical properties, we're talking about characteristics of matter that are not associated with a change in the chemical composition. Things that we'd be looking for would be density, color, hardness, melting points, boiling points, and electrical conductivity. These are all examples of physical properties. Now, a physical change is something where the change in state or the properties of matter occur without any accompanying change in the chemical composition. In other words, like we have here in the candles in Exhibit A, we have candles melting into wax, but if you took that wax and you reformed it and hardened it, you'd be right back to a candle again, for instance. Or you have steam in Exhibit B, water boiling and then condensing on the lid here of this pot, in which you can see the water droplets condensing back into water, that steam condensing back into water. So these are all examples of physical properties and physical changes. Okay, on this slide we're going to take a look at chemical properties. And a chemical property is the change of one type of matter into another type, or its inability to change. For instance, here, if you look on the left side, you've got some rust here, and you know if you leave iron outside exposed to the air that it's going to react with oxygen and moisture and form rust. And as you'll see when we actually do this, rust isn't a deterioration like we would normally think. It's actually gaining mass because you're adding molecules of water and moisture and oxygen to it, particularly oxygen. So rust actually gets heavier rather than lighter. We always tend to think that it's decomposing, but here, this would be a chemical property of iron is that it rusts. Whereas something like chromium here on the right side, as you see on this, probably a nice Harley Davidson motorcycle, you've got all this nice chromium, and one of the characteristics here is you can leave it exposed to oxygen and it doesn't rust. So iron rusts in the presence of oxygen, chromium does not. So these are some examples of chemical properties. Okay, so on this slide here, we're taking a look at chemical change. Now, how do we identify that we have a chemical change? Well, to take a look, we really need to identify something like a product that's new, like you take some reactants and you produce something new on the product side that didn't exist before. So the definition they give in the text is that it produces one or more types of matter that differ from the matter that was present before the change. Okay, so here they give you several examples. If we look here at Exhibit A, they took some copper metal and they put it in HNO3 nitric acid, and as you can see, it forms this bluish copper nitrate solution, and then up above here you can see this brown gaseous nitrogen dioxide. Okay, and that's kind of a dangerous gas. So if we look at Exhibit B, we've got a matchstick, and the cellulose that makes up the wood in the matchstick is going to react with oxygen from the air and produce a chemical change. It's going to release carbon dioxide gas and water vapor. Now we don't see the water vapor. It's so hot it actually evaporates rather quickly. And the carbon dioxide's a colorless gas. It's clear. We would actually have to collect it and catch it. And carbon dioxide, as you'll learn, is heavier than oxygen. So it's actually falling down. It's not going up. It's falling down. And then C here, Exhibit C, we're looking at meat. Kind of ugly looking meat, but if we had all of this meat cooking in a frying pan, you know it's red to begin with. And the iron in myoglobin actually is going to oxidize, and that's where you get that red to brown color change when you're cooking meat on the stove. So you don't tend to think of cooking some foods like meat and such as a chemical change, but it is because you're actually changing some of the characteristics of it. In this case here, the myoglobin in the blood. So we look at Exhibit D here. You got some bananas that have turned brown, and like it says, you get a new form of a banana, I guess, afterwards. As it gets exposed to the air and it oxidizes, it starts to turn brown. They say it tastes less tasty. I don't know. If you make some pretty good banana bread with it, it might not be so bad. But at any rate, those are all examples of chemical change. Okay, before we go on to this slide, let's go back 1 second and let's talk about extensive and intensive properties. And I'm going to write this here on this slide. So, two terms, extensive and intensive properties. Extensive properties. And I'll write intensive properties over here. And we'll put some characteristics down. Now, let's start with extensive on the left side here. So an extensive property is something that does not, it does depend on the amount of matter present. Depends on the amount of matter present. In other words, some examples that would be clearly memorable would be mass, right? If you have more mass of something, that's going to be an extensive property, right? Because it's going to be heavier than something that has less mass. Volume, if you have a 2-liter bottle of soda, that's extensive because it's going to have more volume than a 1-liter bottle of soda, for instance. So it depends on how much you have. So any characteristic like mass, volume, and there's probably a list of them in your text, will be examples of extensive property. They're related to how much of it you have. Now, intensive properties do not depend on the amount present. Do not depend on the amount present. Okay, so an example would be temperature, right? Let's see. If I took water, let's say I took a little bit of water and I put it in a block and I made an ice cube, okay? And that's going to freeze at what? Below less than 32 degrees Fahrenheit, right? Or 0 degrees Celsius. So we've got a ice cube here, and if I have a giant iceberg, okay, and let's say this is a giant iceberg. Well, what's the temperature? We're going to say that's pure water. What's the temperature of this pure water iceberg going to freeze at? Well, it's going to freeze at the same temperature, 32 degrees Fahrenheit. So in other words, the more of it that I have doesn't really change this property of it at all. The property of water is that it's going to freeze at 32 degrees Fahrenheit or less. Whether you have a little bit of it, like in the ice cube, or you have a gigantic amount of it, as in an iceberg. So that's an intensive property. It's something that's not going to change whether you have more or less of it. It's something that's always going to be the same. You'll see this with things like density is probably a pretty good example. The density of a fluid, whether you have a lot of it or a little bit of it, that's another thing that's not going to change. The value for the density of that particular item is going to remain the same. There's lots of intensive properties, and we'll talk more about those in class. Okay, let's go ahead on to that next slide. Okay, on this slide here, and we'll see this often, this chemical symbol on the stock bottles and the chemical bottles that we utilize in class. And so this is created by the National Fire Protection Agency, NFPA, and it's called the hazard diamond. And there's essentially 4 parts to it. You've got the red square, which is your fire hazard. You've got the blue square, which is your health hazard, the yellow square, which talks about reactivity, and then the bottom white square, which are specific hazards. So let's take a look at these a little bit in detail. So if you look at this red block up here, the fire hazard, this is about flashpoints. So the number here, 4, if there's a 4 in here, it means that it's going to burst into flames, if you will, or it could burst into flames as low as a temperature of 73 degrees Fahrenheit. Okay. If it were a 3 in the box, it means it would be a slightly higher number, less risk, and that it would not flash below 100 degrees Fahrenheit. If it had a 2, it would be somewhere above 100, but not in excess of 200. And then if there was a 1, it would, be above 200. And if there's a 0, it just, no matter what, it's not going to catch on fire or burn. So in essence, for all of these numbers here, the higher the number, no matter which block it is, the higher the number, the more danger you are at. So that's something good to keep in mind here. And again, like I said, 4, 73 degrees, 100, 100 to 200, and then excess of 200. Over here in the yellow block, if you look at reactivity, if there's a 4 there, it means it may detonate, could easily explode. 3, shock and heat could possibly detonate it. 2, violent chemical change. 1, it could be slightly unstable if heated, meaning bad things could happen when you heat it in a petri dish or a crucible. And then 0, it's stable, you don't have too much to worry about. Over here in this block, 3, health hazard. 4, deadly. 3, extreme danger. 2, hazardous. 1, slightly hazardous. And 0, normal material. So you can see the potentials for health hazards. Now, a lot of the stuff we have here is usually 1, 2, and 3. We get a lot of 2s and 3s. Off the top of my head, I don't know of any 4s that we have lying around anywhere, or excuse me, not lying around, but locked up. But anyway, keep your eyes open for these things because they do give you some information, and you sometimes have to think about all of these in relation to each other. For instance, it could be a 3 here, which means it's extremely dangerous, that it'll flash at a very low temperature, so it's extremely dangerous, and it can catch on fire at room temperature, plus it can easily react with something else. So this is something that you'd have to really pay attention to. And then here, it might give you some specific information on what might be the really bad health hazard. So we look down here and you get the W, use no water. So in other words, if this were to catch on fire, for instance, because of the low fire hazard, you wouldn't want to throw water on this thing because it may exacerbate it. It may cause it to explode or violently react, or make the situation worse. So if you see the W there with the bar through it, means you don't use water on it to clean it up, or to put the fire out, or whatever the situation may be. Other things you may see, like OX for oxidizer, AC for an acid, ALK for alkalis, CRO that it's corrosive, and radioactive, and we do have some of that, which we'll get to work with throughout the course. You might see that symbol in there as well. Okay, so this is the again, the National Fire Protection Agency Hazard Diamond, and it's good to know and be familiar with when you work with the chemicals in the classroom. All right, so the final slide for this presentation here, the periodic table. We're going to obviously spend a lot of time. You're going to be intimately familiar with the periodic table by the end of the course. You will know so much. I'd be able to pull an element off of here and ask you to give me a whole bunch of information and describe its characteristics and what it's like and how it would react and what it would react with, and you'd be able to throw all of that out. In other words, you're going to learn how to work with this thing, not where just stuff is located. You're actually going to be able to utilize this as a tool, and that's going to be a very important skill for you when you go to college, because most all of you are going to be taking chemistry again, or dealing with it in a more intimate basis. If you go into healthcare or science or maths, you'll probably become very familiar with chemistry. But in a nutshell, and you'll have your own periodic table, and I always let you use your own periodic table on tests and such like that, so it's not a problem. You don't need to memorize it, but you'll become very familiar with it. Generally, it's grouped. We always think about the metals here off to this left side, all of these lightly colored boxes. And the general characteristic for metals, real basically, is that they are good conductors of electricity, and they're also good conductors of heat. You also have the metalloids right in here, and they're they call them semiconductors a lot of times because they're semi good conductors of heat and semi good conductors of electricity. And of course, the most famous semiconductor, silicon, is right here, which is utilized in a lot of our electronic devices to power them up because while it doesn't generate a tremendous amount of electrical current, it can generate electrical current, which is a good thing, but it doesn't get as hot, right? Can you imagine if your cell phone was made out of a metal? It would be burning right through the case with all the energy that's running through it. So we use semiconductors as processors and things like that in small handheld devices. And then off to the right side here in these light green boxes, we have the nonmetals. And of course, those are poor conductors of heat and electricity, and they're kind of the opposite of the metals in many ways. And you can see there's going to be all kinds of codes and stuff on the periodic table that you'll learn what they mean and how to work with them and what each column on the periodic table is called and what they mean and what their valence shells look like. So there's going to be lots of stuff to learn with the periodic table as we go through this course. And always remember hydrogen, even though it's placed over here in this very first column, notice that it's green. It's generally considered a non-metal. It's just over here at the top of the first column because it makes sense there as far as its valence electron shell. So it's placed here because of its electron shell, even though it tends to act like a non-metal really, and it should be, it could oftentimes be considered as right here depending on what kind of a periodic table you look at, and there are variations of this as well. And that's it for this section, so I hope you enjoy it and review this if you need to again. Thank you.